Welcome to the lecture on plate tectonics. The plate tectonics theory is one that says Earth's surface is divided into a few large, thick plates that move slowly and change in size. There also are quite a few smaller plates. At the leading edge of these plates, you get a lot of geologic activity, earthquakes, volcanoes, and it isn't the original theory. The original theory was continental drift, and then we added seafloor spreading to it. We'll go into that, well, now. We can summarize the entire idea in this one picture. Here's the picture from your book. Stuff down here gets hot. When it gets hot, it becomes less dense. When it becomes less dense, it starts rising because less dense material really will rise. Again, imagine yourself keeping an inner tube on the bottom of your swimming pool. You can't do it. In the same way, less dense rock here rises to the mid-ocean ridge, spreads apart, and then eventually the world would get bigger if this stuff didn't get eaten back up into what we call a convection cell cycle, either at a trench, ocean-ocean, or ocean and continent. This graphic is a little bit more complete, and it shows island arcs along ocean-ocean collision boundaries or convergent boundaries. It shows the transform plate boundary where things are sliding, divergent plate boundary, and it shows how volcanoes form when you get subducting ocean plate here. And you also get some rift valleys where this going down spreads the continent apart. But we're getting ahead of ourselves. This is the present theory. We've got a lot of major plates. They are moving. The plates consist of the crust, of course, and the upper portion of the mantle. Those two together are called the asthenosphere. It began with this guy. Okay, it probably began earlier with every student who was sitting in a classroom looking at the world map and getting bored. Think back to third grade, you're getting bored, you're looking at the world map and you notice, gee, you could move Europe and Africa right over to North America and South America and they would fit. If you're like me, your teacher just said, oh, that's just a coincidence. No, it's not a coincidence. And Alfred Wegener, who really does have a face, except in this picture, and his partner in the 1930s started proposing the idea that continents moved across the face of the earth. What he didn't know was that there were plates. His idea was that the continents actually plowed their way through the ocean. And nobody knew how that happened. It was a good idea, but there was no mechanism for it. So he even doubted his own theory. He died in the 1930s in Greenland on an expedition, calling his idea geopoetry. He was a heavy smoker. His sled got stuck, if I recall correctly, and he and his partner were trying to get their way back to camp, and it looks like he died of a heart attack. He really wasn't a geologist. He was a weather person, meteorologist from Germany. Okay, early continental drift. We already noted that continents look like they fit together, but he had noted that fossils were found on two continents, and this was a fossil of a Mesosaurus that couldn't swim. How could it end up on two continents which today are not near each other at all, unless those continents were at one time joined? He also noticed that there were coal beds on different continents that seemed to have the same layers. There were also old climates. Oh, one more time. More fossils. The fossils of the I can do this. Cynogathus. Okay, this, Glossopteris, and Mesosaurus are found like this, and all of them must at one time been joined on the continents. Here was Wegener's idea that the lightweight continent really plowed its way through the denser mantle and just wrinkled this up somehow. It wasn't right. The general idea was correct, but one of the neat things about science is we take the idea and we refine it and we get more and more close to the correct answer. We don't say this is it, and that's what it is. Things can change, which is a neat thing. Now, Wegener named the early original continent Pangaea. He didn't know that before Pangaea there were probably other supercontinents. His idea was that Pangaea separated to Laurasia the northern part, and Gondwanaland, the southern part. And again, here are the glaciation patterns that he observed. Same glacial patterns on 5 different pieces of the earth. I would say continents, but India isn't really a continent. It has since bumped into Asia, even though it's not part of Asia. And again, here are geologic formations and ice formations on 2 different continents. Here is Wegener's idea. Pangaea breaks into Laurasia about 200 million years ago, and Gondwanaland by the middle of the dinosaur times, Jurassic period, then Cretaceous, and then present day. But again, he had no idea what was driving this. He thought the continents were just moving around. He had no idea of what was underneath the waters. That wouldn't come until we started looking for submarines in World War II. He didn't even have an idea of the pattern of the earthquakes and volcanoes, because that came out of World War II with Charles Richter and the seismograph. By the way, that is your books or a book's version of this. This is real data that I gathered from the National Earthquake Information Center last week for earthquakes around the world. He had no idea of paleomagnetism. Now, paleomagnetism is the idea that when a liquid lava solidifies, the iron particles in that lava will take the orientation of the Earth's magnetic field at the time they solidify. We're going to skip past this because it's not really that significant. But what is important, and we studied this in Earth Science 1, is that the North Pole of the Earth really is moving. This is where it was in 1994, this is where it was in 1831, and right now it's somewhere off this island which is known as Elef Rignis, way north of Hudson Bay. World War II, Harry Hess, searching for submarines, looking at the bottom of the seafloor, came up with an idea. No, not the lava lamp, but his idea was related to this. How does a lava lamp work? There's a light bulb down here, one of the old-fashioned incandescent light bulbs. It gets really hot. If you still have those bulbs in your house, you know what I'm talking about. They hurt to touch when they're on. This gets really hot. It heats the glycerin, which I believe that is in here. The glycerin, which is immiscible or doesn't dissolve in this liquid, gets less dense and it rises. Then it cools and comes back down. His idea was that the core of the Earth is hot. It heats the mantle rises and creates this ridge, which he had actually measured by doing testing when he was looking for submarines in World War II. And then through a convection cycle, we end up with circles going on in the mantle. Now, this is kind of curious. We don't find any rocks on the seafloor that are older than 200 million years old. How can that be explained? Because the rocks rise here, they form, and then they sink underneath us. Again, we're on the lighter crust. This is more dense material. They subduct. Now, the continental crust is fairly thick, 30 to 50 kilometers thick. Earthquake waves average about 6 kilometers a second. The oceanic crust, earthquake waves go a little bit thicker or faster, and the oceanic crust is thin compared with us. We float on it again because we are less dense. There's no way you can get this stuff to go underneath, not unless you force it somehow. Now, this is an interesting idea too. Isostasy we'll get into again later, but if you put more stuff on this, it's going to bounce deeper. If you take these mountains off, this continent will bounce back. This is what Harry Hess was studying, the age of the ocean floor. Okay, and looking for submarines. But he found out that near the middle, the ocean floor is fairly young. As you move out on either side, the rocks themselves get older. But again, nothing older than 200 million years. Also, The crust right here is very high. It sinks on either side of this lava plume or mantle plume. Also, the sediments are really thick on either side, but very thin along the ridges. By now it seems fairly obvious to us what's going on. Here is what's going on with magnetic reversals. When the plume rises, the iron particles in the rock take the orientation of the Earth's poles at that time. Now, as you may know, Earth's poles reverse from time to time. So new rock coming up will take the orientation of that new orientation. So what we find is, as we move away from the mid-ocean ridge, reversals. And the reversals are exactly the same on either side. How could that happen? Something coming up here, splitting both directions. This is the same image from your book. Younger rock near the ridge, older rock further away. And because geologists have really good imaginations, they have named all these epochs or time periods. They really get into it. Now, one place where the mid-ocean ridge rises above the ocean is in Iceland. Okay, also the Azores and a few other places. But Iceland rises above the ocean and is being ripped apart. This is the actual mid-ocean ridge right here, sticking above the ocean, and Icelanders, being what they are, stuck a nice trail through this. They even have geothermal plants that gather heat out of this and create their electricity. And they measure the movement of it. Here's an Icelandic fellow with a radio geophone type thing that measures all this motion. Now, how much motion is going on? We've actually measured it now. Thanks to satellites, this is the direction and the relative speed that the plates are moving. Where do we see the fastest movement? Well, not down here. Take a look at the Middle Pacific. Relatively fast motion. Take a look over here at the Himalayas, fairly fast, where India is bumping into Asia and creating, well, some wrinkles here. Like if you lay a towel on top of your table and then squish the sides of the towel together, you're going to get something like the Himalayas or the Alps or the Andes or the Rockies or even the, I think I covered them all. Okay, one more type of fault. You have a transform fault here where along the mid-ocean ridge, the plates are slipping past each other. This cliff here is called an escarpment or escarp. Let's talk about types of plate boundaries. You have divergent plate boundaries in which plates move apart from each other. When they move apart, you get a rift and hot stuff coming up. With that hot stuff, quite often you get metals. This is what's happening in Africa right now with the Great Rift Valley, and there are lots of volcanoes in there. This is what's happening along the Red Sea. And here's what's happening along the Atlantic Ocean. Again, younger rock near the middle, older rock near the edge. Very few sediments right here. Lots of sediments as you get over to the side. Here's the Rift Valley of Africa. And right here, there seems to be a plume that's ripping apart the crust of the Earth, splitting in a three-way split. There's a satellite view of the area. Now, we better pause here. I'll be right back on the other side.